Hi everyone, welcome to another episode of Classes with Atish. In this episode, I'm going to do something different. I'm going to correct a mistake that I did in one of my previous episodes. That episode was named Linear Momentum and Conservation of Linear Momentum. Towards the end of that episode, I showed an example in which most of it was correct, but there was a small error that crept in, and I want to correct myself on that today. Okay, so with that, let's restate the problem one more time. Okay. In this arrangement, we have a bigger block of 10 m and a small block of mass m. And this surface, as well as the surface on which the bigger block is resting, both are frictionless. This mass m is let go from the top, so obviously it would slide down this curve. Now, this curve is that of a quarter circle. Okay, so basically, this radius is given as r. Okay, so once the mass reaches here, so it will slide down here. When it leaves this bigger block, it will leave with some velocity. Our goal is to find out what is that velocity. Okay, so with this, let's get started in solving this problem. First up, let us assume that this velocity is v. Okay, now this bigger block will also get a velocity in the opposite direction. Let this velocity be u. Okay, now let us look at what we can apply to get to the value of v. Okay, first up, let's look at this problem and see if the net force acting on this system, the system being the 10m plus m combined, whether the net force acting on the system is 0. Is F net equal to 0? Well, to figure that out, let's quickly do a free body diagram of each of these masses. Now let's say this mass has slid down to this position. Okay. There will be a force due to gravity, small mg. There is no friction. However, there is a normal reaction from this surface. Let's call that normal reaction N. Okay, these are the only two forces that are acting on this small m. Okay, now for the big M, which is 10m, we have force due to gravity, which is 10 mg. Then we have reaction from this ground. Let's call that R. Now, there is no friction, so there is no force here, but there is one force. This N is the reaction that this body 10m gives on m. So based on Newton's third law of motion, the small m will also give an equal and opposite reaction to this, which is same as the normal force N. Okay. Now, net external force. Now, N is an internal force, so we need not consider that. But we still have net external force 10 mg, mg and R. So we cannot say F net is 0. The answer to this is no, it is not 0. However, what we can say is F net in the x direction is 0. If we consider this is the x direction, Fx is 0, Fy is not 0. So if that is the case, then if F net is 0, then we can apply conservation of linear momentum in the x direction. So this will give us Px, which is momentum of the system in the x direction, is conserved. So Pxi should be equal to Px final, initial equal to final. Now initially both these bodies were at rest. So we can say initial momentum is 0. The final momentum is the small m leaves the body with velocity v. This velocity v is with respect to ground. The bigger body 10m is moving to the left with velocity u. Again, this u is with respect to ground. So we can write mv in the positive direction minus 10m u. So we can cancel out m's and basically we get this relation v equals 10u. Okay. Now our purpose was to find v. We got a relation, but we don't know u. We have two unknowns. So let's just say this is equation number 1. So what else can we apply to this? Now let's look at work energy theorem. Work energy theorem. Now this is such an important theorem, and it's very important to understand what this theorem says. So let's revise that. Work done by all forces is equal to the change in kinetic energy. Okay, many concepts are embedded in this. Now, what are all my forces? So let me write all the forces here. It's already given here. So all the forces in the system is work done by mg gravity, work done by 10 mg gravity. These two we taken care of. Then work done by normal reaction, let's say on m, because of the displacement of m, small m. What's the work done by this normal reaction? This normal reaction is different than this, okay? So we have to also look at that work done by normal reaction, that is on 10m, plus work done by this reaction force R, which the ground is pushing on this 10m. All of this should be equal to the change in kinetic energy. The work energy theorem says that work done by all forces include external forces, internal forces, conservative forces, non-conservative forces. It also includes pseudo force if your frame of reference was a non-inertial frame. However, this kinetic energy that we are looking, we would be using V and U, right? And these are from the ground. So it is an inertial frame. So we do not need to look at pseudo forces here, work done by pseudo forces, because we are looking at the entire system. We are not looking at just M. If we were just looking at M, then it might be a non-inertial frame of reference because the 10m itself is accelerating. Okay, so we don't have to look at pseudo forces, but it's important to look at all these work dones. Now in the previous video, the mistake that I did was I did not investigate this part in detail. I assumed the work done by this normal force on 10m is 0. That was a mistake. Okay, let's get to that. But before that, let's solve the other ones. Now, work done by mg, okay, is the force of gravity is downward and the net displacement in the y direction is r because the mass came down by r. So this is nothing but mgr. Easy one. Work done by 10 mg on the big mass. Now, if I just look at this big mass, does the center of mass move for this? Yes, it moves in the x direction, but not in the y direction. Now, since displacement is in the x direction, but this force of gravity is in the y direction, the net work done by this gravity on 10 mg is 0. Okay? All right. Now let's look at this normal reaction that is working on this small m. Okay? This normal reaction is this direction. This small m, every displacement that is happening is perpendicular to the normal reaction. So this work done is also 0. Okay? We'll think about this in a little while. Similarly, what's the work done by this reaction R that the ground is giving on 10m? Again, this is in y direction. The displacement of 10m is in the x direction. So this one is 0. And that is equal to the change in kinetic energy. Change in kinetic energy is half mv square. The small m left the body with velocity v. And the other one is half 10m minus u square. So we can actually write u square. Now the missing link then is what's the work done by this normal reaction on 10m. Okay? Okay. Now let's investigate this normal force in a little bit more detail. Okay? Now let's read out this thing. Okay? When this small m is here, at the very top, this normal force is 0. Would you agree? Because there is no, it is not pushing on the bigger block. But as it starts to slide down, the normal force increases. Okay? As it starts to slide down, the normal force increases and it is always perpendicular to that tangent at that point. Okay? So it keeps on increasing, and when the block is here, it is maximum. Okay? Now, let's investigate this little more closely. Now let's say at any point the normal force that this 10m experiences in this direction. Okay? So this is the part of the circle or quarter circle. Let's say if I draw a horizontal, this is the angle theta that n makes with the horizontal. So this theta varies from 0 when it was at the top to pi by 2 when it came here on 90 degree. Okay? Now, this n is a function of theta. more theta increases, normal force increases. How can we find that function? Now let's take a look at the small m. Okay, maybe I will draw it here. This small m, there is force of gravity, and this normal reaction is this way. If I draw the same horizontal here, okay, so we said this angle is theta, so this angle is now theta, okay, and obviously this is 90 minus theta, pi by 2 minus theta, okay. Now this mass does not leave the surface, so the component of mg in the direction of n must be balancing that force. So mg cos pi by 2 minus theta, which is mg sin theta, must be equal to n. Now then we can write n is equal to mg cos pi by 2 minus theta, or we can write mg sin theta. So we got n as a function of theta. Obviously at 0 sin theta is 0, so n is 0 at this point, and when theta is pi by 2, sin theta is 1, so n is equal to mg at this point. So it makes sense. Now, what will be the work done? Let's say a small work done by this normal force on 10 mg. Okay. When, let's say at some point, it had already reached a distance x, and now it moves by a small distance dx. Okay, so then we can write n dx, which is mg sin theta dx. Now, another conceptual thing will come in. If the big mass moves by dx, how much does this small mass move on that side? Now see, conservation of linear momentum is what we applied here. Now conservation of linear momentum applies at all points between this and this, not just the initial and final point. So at any point, this will still apply. So which means if at this point the small m had a velocity vm, the big mass had a velocity u10m, this relation would still be there. So from this, we can further say that if the 10m moved by dx distance, 10m u moved by dx distance, so 10 times dx would be equals to whatever the small m moved, ds. So from this, we can further write that this is equals to n ds by 10, where ds is what the small m now is moving in this direction, corresponding to a small displacement by the big mass moving in the opposite direction. Now still we are not out of the weeds, because I have to find out ds in terms of d theta. Okay, now comes a little bit of geometry. Okay, now let's look at this part in a little bit more detail. Okay, so let's say this was the center of the quarter circle, and this one was the part of the quarter circle. Let's say we are examining at any point. So let's say at some point we said it is at angle theta with the horizontal. So the body is right here. Okay. Let's say for a small d theta angle, this ds displacement happened, which means what? The body moved from here to here. So this in the horizontal, in the x direction, this distance is ds. Now the radius is r. So we can approximate this curve as a straight line. So this distance is r d theta. Okay. Now look at this small triangle here. If this angle is theta, this angle is also theta, which means this is 90 minus theta, or this angle is theta. Okay. Now I can see some light here. Sine theta. Look at this triangle, small triangle. Sine theta is ds by r d theta. Or we can write ds is r sine theta d theta. Okay, there's a little bit geometry here, but if you get this, everything else is simple. So then we can replace ds by r sine theta d theta and n by mg sine theta. So mg by 10 sine theta r sine theta d theta. Or we can also write this as mgr by 10 sine square theta d theta. So then if we integrate to find the total work done, will be, now theta is moving from 0 to pi by 2, integral 0 to pi by 2 mgr by 10, which is a constant, sine square theta d theta. Now I will not go into the integration part, but the answer to that is mgr by 10 theta by 2 minus sine 2 theta by 4. And this range is from 0 to pi by 2. Okay, so the work done by this normal force, then we had put a question mark here. Because of lack of space, I will write it here. So this is mgr by 10 theta pi by 4 minus sine 2 theta is 2 pi by 2 is sine pi, pi is 0, so minus 0, minus 0 by 2 is 0 and sine 0 is 0. So we can just say this. So now then we get a relation here, mgr. We are just now substituted everything. So on the left side we have mgr and this. So we can say mgr, so 1 plus pi by 40 is equal to this term. So let's say half m, if we take constant, is v square plus 10 u square. M and m gets cancelled. Let's move 2 on the other side. So 2gr 1 plus pi by 40 gives us v square plus 10 u square. So this is equation number 2. So from that, now if you substitute v square is 100 u square, So this is 110 u square, or you can get u as gr by 55, you move that side, 1 plus pi by 40 square root of that. So if you got u, v is 10u, so 10 times gr by 55, 1 plus pi by 40. Okay, so let me know what you think about this solution. Hopefully I got this correct. The mistake that we did was, again to restate that, is the work done by this normal reaction on 10M is not a zero, which we assumed zero in our previous problem. So this, if we consider, then the correct solution is that. Let me know what you think and leave some comments, and I will see you in the next episode. Cheers.